Welcome everyone. Today we are going to study about the superposition of simple harmonic motions, and this is included in the semester 2 paper CC4 according to the Calcutta University syllabus. So firstly, let's recap that we have already discussed in detail the superposition of two SHMs of the same frequency acting at right angles. So now if the frequencies are slightly different, then what will happen? So if the two harmonic vibrations superposed at right angles have slightly unequal frequencies, the resultant pattern will pass through all the phases which we have discussed earlier. So earlier we saw that we are taking two simple harmonic motions and then we superpose them, and both of the simple harmonic motions are acting at right angles and they have the same frequency. So after superposition we see the mathematically how the resultant behaves, and from that we also saw the pictorial representation. So now if the two frequencies are slightly unequal, then the resultant pattern will pass through all the phases which we have discussed earlier. Why? Because the faster will gain in phase over the slower, and the pattern though will be similar to the previous case when the two frequencies are equal. However, now what will happen is that due to the gradually changing phases, the pattern will constantly change with time. However, always it will remain confined within the rectangle formed by 2A and 2B. Now, and slowly the pattern will change, say from a straight line when this phase difference is 0 initially, and then it will open up into an ellipse, and after that pass to a circle if A equal to B when the phase difference is 90 degree, and after that it will become an oblique ellipse inclined to the left, and again when the phase difference is 180 degree it will become a straight line inclined at 135 degree to the positive x-axis. So graphically you can get a representation like this. So here this is the initially when delta equal to 0, like I told, it will be a straight line. After that, when the phase difference is pi by 4, I am getting an oblique ellipse. Then pi by 2, I am getting a representation like this, and specifically if A equal to B, then it will be a circle. After that, again in 3 pi by 4, again an oblique ellipse inclined on the other side, and at pi again a straight line. And after that, if I increase, this will go on in reverse till 2 pi. So here I am seeing that previously I saw when the two frequencies were equal, then I saw the mathematical behavior and the graphical illustration. Now when the two frequencies are slightly different, the pattern will constantly change with time and it will pass through all of the phases which we discussed earlier. And we are already seeing the graphical representation here and how we get it in a likewise to what we discussed in detail previously. So such a changing pattern enables the frequency difference to be determined. If the changes are completed in n seconds, then the frequency difference will be 1 by n. And obviously if I know one of the frequencies, then I can determine the other. Now, what are Lissajous figures? So the curves formed by the superposition of two simple harmonic motions acting at right angles are known as Lissajous figures. This is very important topic, and particularly if the ratio of these frequencies are the ratio of two small integers, then there is a particular importance attached to this. Now the resultant curve which will be formed by the superposition, the slope of that depends on what? That will depend on this ratio of frequencies as well as the position and the phase relation at the initial moment. And already we have whatever examples we have discussed so far, all of them are examples of Lissajous figures. So the curves formed by the superposition of two simple harmonic motions at right angles are called Lissajous figures. Now, if the ratio of frequencies is nearly equal to that of two integers, then what happens? So when the ratios of the frequencies is nearly but not exactly that of two integers, then the orbit will gradually pass to the various phases of the case in which the ratio is exactly that of the two integers. And this will then repeat in the reverse order like we just saw previously. And this cycle of changes are then again repeated. So below we will see the pictorial representations when the ratios are 1:2, 1:3 and 2:3. And already the 1:1 we have discussed in detail previously. So these plots are a bit unclear, but you will get a clear version in the uploaded notes. Kindly check with that. So here this is the pictorial representation of how the phase is changing. As I am changing delta from 0 to pi by 4, then pi by 2, 3 pi by 4 and pi. How the behavior is changing. I have shown here for three ratios of frequencies, 1:2, 1:3 and 2:3. And of course we'll study one case of this in detail, and all the other cases can be obtained in a likewise manner. So now from this plot, herein I can tell about the usefulness of Lissajous figures. So from this curve, from this Lissajous curve, I can obtain the ratio of the frequencies, which is a very important use of this Lissajous figure. So how do I do that? So I draw a horizontal and a vertical line to cut the curve, and I find out the number of intersection points this makes each means the horizontal line and the vertical line makes with the curve. And then the ratio of the number of intersections on the horizontal to that of the vertical line is the ratio of the corresponding periods, and from there I get the required ratio. So how do I get it? So say here, say in this plot, if I draw a horizontal line, then it is cutting at 1 point. And if I draw a vertical line, it will cut at 2 points. So I take the ratio horizontal to vertical, ratio is 1:2. And likewise for each plot. So this is a very important use of Lissajous figure. And also the ratio of the amplitudes is the ratio of the sides of the rectangle containing the figure. From there, from the sides of the rectangle which contains the figure, I am getting the ratio of the amplitude also. So now already 1:1 frequency ratio we have done the mathematical derivation in detail, and we have studied the graphical illustration also. Now let's study one more ratio, frequency ratio, in detail. So here I will see the case Lissajous figure for frequency ratio 1:2. So let us represent the two simple harmonic oscillations by x equal to a cos omega t and y equal to b cos 2 omega t plus phi. So now from representing this is equation 1 and equation 2. So from equation 1 I get that cos omega t is x by a. So obviously what is sin omega t? Root 1 minus cos square theta. So root 1 minus x square by a square, which is given by this. Now from equation 2 also similarly I am getting that cos 2 omega t plus phi is y by b. And we all know the formula for cos a plus b. Cos a cos b minus sin a sin b. That is equal to y by b. Again I am using another mathematical identity that cos 2 theta is 2 cos square theta minus 1. And sin 2 theta is 2 sin theta cos theta. So I substitute that here, and then what do? I already obtained from equation 1 cos omega t equal to x by a. I put that here and I obtain the value of sin omega t, which I am substituting over here. So I get equation like this. Now I square both sides. Okay, so a minus b square, this full thing square here, cos square phi minus 2ab plus b square, and the right side also squared similarly. So then I collect like terms and I bring in the terms of cos square phi and sin square phi, so that I can use the identity cos square phi plus sin square phi equal to 1, and from there finally I get this equation. Okay, now I take some things common, and finally I am getting the equation of the resultant path as this. So this, when the two SHMs having frequency ratio 1:2, they are superimposed, then we get the resultant equation, resultant path as this. So now let us study some particular cases of this. So firstly, case 1, when this phase difference is 0, then what will happen? I put phi equal to 0 in this equation 3, and I get here that equation of this form. So this equation, let's recall that this equation is of the form x square equal to 4ay, which we studied, parabola equation. And since there is a square, so this represents two coincident parabolas. Okay, an equation of each parabola will obviously be given by this, or x square equal to a square by 2b in bracket y plus b, and I will see the graphical illustration of that. Let's study one more special case when phi equal to pi by 2. Substitute that here, then I get a curve of this type, an equation of this type, and this represents a curve having this type of form. So obviously a very good exercise will be, if you try this in GNU plot, then you will get the graphical behavior of a mathematical equation of this form to be this. And the first one, so these two plots, the first one is the phase difference 0 case, phi 0, which is with the behavior will be as we discussed like a parabola, which is this, and the next one is phi equal to pi by 2, and I get the behavior to be of this form. Now let's move on to another important thing, which is an uniform circular motion is equivalent to two simple harmonic motions acting at right angles to each other. So if I take two motions represented by x equal to a sin omega t and x equal to a cos omega t, how much phase difference is there between the two? They differ from each other by a phase difference of pi by 2. So because cos omega t is sin omega t plus pi by 2, so the second one is leading in phase over the previous one, because cos omega t is sin omega t plus pi by 2. And if I take two motions like x equal to a sin omega t and x equal to minus a sin omega t, then they are in opposite phase, because minus sin omega t is equal to sin omega t plus minus pi, sorry. And we can easily see that these two motions, x equal to a sin omega t and y equal to a cos omega t, having the same frequency omega and same amplitude a, but they have a phase difference of pi by 2, so they combine to give a circular motion of radius a, because x square plus y square I am getting from here equal to a square. Now in which sense this circular motion is being covered, in a clockwise sense or anti-clockwise sense? How do I understand that? So to understand that, let me first put t equal to 0. So if I put t equal to 0, then what will happen here? Then x is equal to 0 and y equal to a. Okay. So graphically I can tell that I am at point P1 where x is 0 and y equal to a. Now as I am increasing t, suppose say small t reaches the value of capital T by 4, where capital T is the time period. So what is omega into t? Omega is 2 pi by capital T into capital T by 4, so pi by 2. So if you put pi by 2 in those two equations, you get x equal to a and y equal to 0. So now you've reached point 2. The particle is at point 2, at point P2. So from P1 I have traveled to P2. So the circle is being covered in a clockwise sense. Similarly, if I study the motions x equal to a sine omega t and y equal to minus a cos omega t, then I will see that this will represent a circular motion described in an anti-clockwise sense. So we pause here today, and next day we will see some important problems to understand the picture even better. Thank you.